So, hi everyone, welcome back. So in this section, we'll have two speakers before the lunch break, and both of them are very young researchers, and the focus is mostly on the learning side of tactile sensing. So the first speaker here is Dr. Kroemer. So Kroemer is a postdoctoral researcher at the University of Southern California, and he works together with Professor Gaurav. Okay, his research interests are in machine learning and robotics, with a focus on learning grasping and manipulation skills. So today, he's going to give a talk on learning to monitor and adapt the manipulation skills based on tactile events. Let's welcome.
Yes, I'm Kroemer. Can everyone hear me all right? Okay, so as you said, I'm both at the University of Southern California. Soon I'll be starting as a faculty member at CBU. And today I'm going to be talking about monitoring and adapting robust manipulation skills with tactile events. So in the future, we want robots to perform a wide range of different kinds of manipulation skills. We want robots that can take care of the elderly, that can perform household chores, work in restaurants, and also help out in hazardous environments. Now, we want these robots to actually be able to manipulate a wide variety of objects in these unstructured environments. So there's going to be a lot of variability and a lot of uncertainty. However, we still want the robots to be able to perform these skills in a very robust manner. And so it's very important that the robots actually learn to perform some manipulation skills robustly. And a key component of that, I think, is tactile sensing. So tactile sensing is useful for allowing robots to actually monitor manipulation skills. So detect when, or even better, predict when errors are going to occur and be able to recover from them in a timely manner. In this talk, we're going to be focusing mainly on the biotax sensor, which we've already seen earlier this morning. So the key things about the biotax sensor for this talk, at least, are the fact that we have a hardware core with a set of electrodes on it, which are going to allow us to actually measure the skin deformation. And we also have a high-frequency pressure sensor, which allows us to actually detect high-frequency vibrations. And these sort of reflect the slow afferents and fast afferents within the human skin. So it's very inspired, as the name suggests. Now, when we think about tactile sensing for skills, we probably think about sort of the continuous feedback case. So for example, here we have a robot using a significantly cheaper tactile sensor for actually performing a scraping task. And as it's sort of scraping the surface, it's using the tactile signal to adapt the trajectory, such that it gets a nice smooth surface, nice smooth scraping, despite the fact that, for example, we can change the height of this block, make it higher. And so we can actually use this kind of feedback for perturbations. However, I think in tactile sensing, or in manipulation, there's another important kind of feedback that we need to consider from tactile sensing. And that's actually the fact that manipulation tasks are largely a hybrid system which consists of multiple modes. So effectively, we can think of manipulations as having continuous parts with discrete jumps between them, which are often due to contact changes. So for example, if we're grasping an object, we have the following three modes. We sort of have our hand in free space, we have contact with the sides of the object, and we actually have the object in our hand, and we can move it around. And these modes are very important because depending on which mode we're in, we can actually perform different kinds of manipulations. So for example, lifting the object, or actually, if we apply enough sideways force onto the object, we can actually scrape it along the surface. And as I said, there's certain conditions that need to be fulfilled to go from one mode to the next. And these are often resulting from contact changes. And these contacts also create vibrations. So for example, when we make contact, when we break contact, or when we have a sliding contact. And depending on what the task is, we want different mode transitions are going to be either goals or errors. So for example, if we want to pick up an object, then the transition from here to here and from here to here are both considered sub-goals. If we want to actually use the object to scrape a surface, then we're going to need to actually treat this as a sub-goal, and this is an error, so we don't want to break contact. But we still want to monitor for when these events happen. So we get this idea that these tactile sensing is good for actually monitoring the contact changes, and we actually want to detect when, for example, we make, break, or slide contacts, or as well as when these do not occur. So those can also be error cases. And as we also mentioned, a lot of these contact changes are going to result in vibrations. And that's why also, for example, the high frequency component of tactile sensing is very important, I believe. While the other sensing modalities provide additional information about the forces. So in this talk, I'm going to be covering three key parts. So first of all, we're going to be looking at actually predicting grasp failures and learning to regrasp objects. So this is really about predicting when failures are going to occur and actually being able to and actually being able to avoid making those mistakes. We're then going to be looking at detecting object-environment contacts. So that's between a held object and the environment, the kind of contacts, and localizing those. And finally, we're going to look at actually segmenting tasks and detecting mode transitions accordingly. But to begin with, we're going to be looking at predicting grasp failures and learning to regrasp. This project was spearheaded by students Yevgen and Carol. And so what we want to do is we want to actually predict whether a grasp that we've just done is going to be successful. In this case, it means actually picking it up and shaking the object around without dropping it. And we want to be able to predict this as soon as possible if it's going to fail, so that we can actually account for it and effectively avoid making that mistake. Now, in earlier work, we looked at actually grasping the object and trying to classify directly then. However, if you don't actually lift the object, there's a lot of sort of latent information, which is very important for the grasp success. And actually lifting the object up helps to provide some more information. So for example, you can detect its slip. You're going to have the mass distribution can be detected from a slight lift. And so we don't want to just grasp it at the beginning. We don't just want to grasp it and predict the success from the initial grasp, but we actually want to lift it a little bit. And so that's what we did. So we actually had the robot lift the object slightly, as you can see here. And we took measurements of the tactile signal during this time, so 650 milliseconds before and after the lifting event. And we then used these to compute a set of features using spatial temporal hierarchical matching pursuit. So this was a method that was developed in Dieter Fox's lab. And it provides us with a set of hierarchical features, which also includes some spatial and temporal aggregation. So spatial in this case means across the finger. We then had the robot actually learn a classifier based on 1,500 grasp samples with uniformly sampled poses of the hand above the object. So we're only looking at top grasp in this case. And using these features, the robot learned a classifier using support vector machines. Now the thing is, obviously, it's not going to be 100% successful to grasp, especially if we're just doing sort of random grasp above it. So the question really becomes, if we're not going to be successful, what do we do if we fail? So one approach would simply be say, okay, we failed, let's put the object back down and just start over again. However, we're kind of missing a key component there. Because we've already grasped the object, we've gotten more information about it using the tactile signal. So really what we want to do is we want to take that tactile signal from the failed grasp and determine how to adjust our grasp according to that signal. So to do that, we first learned policies for individual objects. So these are regrasping policies. And what we have is we have a policy as shown here. So we take in a set of features. In this case, we take the top 5 principal components of the spatial temporal hierarchical matching pursuit features, I should say STHMP features. And we're using those to predict the 6 changes in the end effector pose. So that's 3 for position and also 3 for the Euler angles. So that gives us, with a linear policy, that gives us a set of 30 parameters which we want to learn. And to learn these parameters, we're using a relative entropy policy search. So this is a reinforcement learning method which was developed in Jan Peter's lab. So as a reward function, we have as follows. So we first, obviously we have to regrasp, so it has to be a failed attempt. We then pick it up slightly and we predict whether it's going to be successful or not. If it says it's going to be unsuccessful, then we give a reward of 0. If it is successful, predicts a success, then we're actually going to lift the object further up and shake it around. If it drops the object, it gets a reward of only 0.5, where if it's an actual successful grasp, we get a reward of 1.0. So using this approach, we can see here some of the trials. So you can see first it fails. Now it's going to try regrasping it. This is the initial random policy, so it's not great. This is just random regrasping. But then after, for example, 4 policy updates, where each policy update has 100 trials, we start getting a little bit better. So again, we have a failed grasp. You can also see a little slip there. And now we're regrasping it. And it generally looks good. So it's a good grasp, but then when we pick it up and we shake it around, we still drop it. But then after, for example, 8 policy updates, we really start getting a robust policy that can reliably regrasp the object. But that was now just learning policies for individual objects. Ideally, we want this policy to actually generalize between different objects that the robot encounters, so that we don't have to sort of retrain every time we learn a new object. So to do this, we looked at actually learning a neural network policy using the samples collected from the initial individual object policies. So for the neural network, we have an input. In this case, we have 20 PCA components, so we allow the robot to capture some more of the details. We have one hidden layer. We actually tried using multiple hidden layers, but because the STHMP features already have this hierarchical structure, there isn't a lot of benefit in having an additional many layers at the neural network level. And at the output, again, we have these changes in our pose as before. So here you can see some of the results from these experiments. So here we have some of the different objects. So the cylinder, box, and ball were training objects, and we also have a new object. And here we have the number of regrasping attempts. So for example, 0 regrasp means that this is the initial success rates for the just trying to pick up the object once. And as you can see, we get roughly 42% success rate. If we then allow the robot to perform 1 regrasp, then we get in the roughly 84%. And as we go for more and more regrasps, we can get higher and higher until we get into the high 90s. Now, this is using just the individual linear policies. If we actually use the combined policy, we get the rewards over here. And so there we get pretty much directly a 90% success rate for 1 regrasp. And it's important to note actually that the success rate is higher using the combined policy rather than the individual object-specific policies. So this indicates that by learning from multiple objects, the robot's actually able to share information that's common between these objects and learn a better overall strategy that works better for the individual objects. We can also see for the new object that we get a 80% or 81%, which is definitely better than just the initial grasp. However, it's obviously not as high as these training objects. So you can see also some of the graphs of these objects. So for example, there you can see it pinches the corner, and then adapts the hand actually, so it's nicely aligned with the 2 sides. Similarly, you can see with the cylinder at the beginning, it's slightly off-centered. It starts tilting a little bit. It actually detects that and then tries regrasping it more stably. We can also see this on the ball object. So at first it's a very high grasp, and you actually see it slipping a little bit there. And then it regrasps it much lower, such that it has a nice stable grasp. Obviously it's not going to go for power grasp in this case because it only has the fingertip tactile sensors. So that was looking at how we can actually detect kind of errors for individual grasps and how we can actually compensate for those. But not all of the contacts and manipulation skills are going to be between the hand and an object. Often we want the robot to be using tools, and we want to be able to detect contacts between the object or held object and another object in the environment. And so we're going to be looking at localizing these contacts with the work from Artem. So, as I said, often we're going to have contacts between the object, held object and the environment. These often correspond to errors. So, for example, when we bump into objects, but they also may be goals. So, for example, when we place an object down. And it seems that humans are actually very good at this. So maybe during this workshop at some point, grab somebody else and sort of have them hold a bottle, close your eyes, and then tap at the different locations on the object. And you're actually very good at localizing where those contact points are. And we want the robot to actually be able to perform a similar kind of capabilities using its tactile sensors in its fingers. So in particular, based on the sort of the vibrations and the forces that we detect, we want a robot to actually be able to estimate the contact points and their normals. So to do this as a learning problem, we first have to collect a lot of data. In this case, we collected tap events using the tool shown here. So this is it's a tool with a poking pointer, Vicon markers, and a force torque sensor. And we'd have the robot holding the object, and then we would tap on lots of different locations on the object. And so for example, here you can see different locations where we tapped on the objects as well as the corresponding normals. Extracting the actual contact events was fairly straightforward by using the high frequency pressure signal. So we simply had to threshold that. And then we extracted a window of around 250 milliseconds after that event as the data for trying to estimate where on the object that contact was made. So Artem actually collected a lot of data using this approach. So here we have the 18 objects that we used, and he collected more than 15,000 tap events across these different objects. And you can see we have different materials. We have some objects that are sort of hollow, some that are filled. So we have a wide variety of different objects that we're interacting with. We looked at a number of different ways of actually formulating this problem as a machine learning problem, and including, for example, support vector machines and Gaussian processes, as well as neural networks. And we looked at this both as a classification problem and as a regression problem. And for the details, I suggest you look at the paper. But the method we found to work the best was actually treating as a classification problem with separate classifiers for each of the 3 position and the 2 normal dimensions. So what we did is we created a neural network classifier where we take the space of all contacts and we put a grid on it. So the grid has 1 centimeter increments and 10-degree increments for the angles. And then we have this neural network classifier, which based on the skin deformation data, it uses 3 hidden layers with 2,000 neurons each, and it predicts which effectively row or slice of that, which slice of that contact space is actually being contacted at that point. And so then we can combine from the 5 different neural networks the estimates to get a single grid cell. So you can see the results of this experiment, where we have the mean absolute errors. So in this case, we did a cross-validation over the objects. So we always trained on 17 of the objects and then tested it on the 1 held out object. And as you can see, we get a mean absolute errors of roughly 2 centimeters for the position and about 15 degrees for the orientation of the normal. Now, if you compare that to, for example, tactile sense errors, then obviously that's a fairly coarse resolution. However, it's important to remember that this is not actually on the skin, but it's on the object. And so we're going through the object, and 2 centimeters is actually, it's about that big. So for detecting where on the object it is, it's actually a fairly accurate estimate. Right now, we've been focusing on single contact points, but in the future, we're going to be looking into more sort of like surface contacts or edge contacts as well. So for the final part of the talk, I'm going to be looking at actually segmenting tasks and detecting mode transitions. And this is the work from Harry Say. So far we've been using different manipulation skills, but the question is actually where did these skills come from? And ideally, we'd actually have skills for transitioning between the different modes, I would say. So as I mentioned before, we have these mode transitions, which tend to end in sort of these contact events, which result in vibrations and changes in the forces. And we really want the robot to actually learn skills that end in these events, such that the robot can learn to detect when they occur and terminate the skill early, or if they don't occur, that it can detect that an error has occurred. So this is also very similar to what we see in humans. This is the work of Johansson and Flanagan. And here we have, similar in the grasping, we have the reaching phase, we have the loading phase, lifting, and holding. And as you can see, when we go from the reaching phase to the loading phase, we get these spikes in the fast afferents, so the high frequency. And similarly, when we go from the loading to the lifting, so we're in break contact, we again get these spikes in the vibration signal. And we want the robot to be able to detect effectively similar kinds of events in different manipulation skills. As our example task, we looked at the peg and hold task. sorry. But in this case, it's a guided peg in the whole task. So we have a board here, which has a number of different geometric features on it. So for example, we have a curved groove, which leads to a hole. We have a straight groove, which leads to a hole. And we have a squared groove, which leads to a hole. And the idea is that we want the robot to actually be able to use these geometric features in order to perform the peg insertion more robustly. And in this case, we're just going to be, for this talk, we're going to be focusing on the curved groove. So for the curved groove, we can identify a number of modes. So for example, we start off in the air. We then make contact with the surface before we slide the peg into the groove. We then trace it to the corner, up to the hole, and then into the bottom of the hole. Now, obviously, in this case, I've sort of predefined what the modes are, but we don't want to do that. Instead, we want the robot to actually segment the task on its own from demonstrations. So here I have an example of a demonstration where the person takes the robot by the hand, makes contact, slides it out to the hole, and then inserts it. To perform the actual segmentation, we've been using Bayesian online change point detection to detect when we have these changes in the signals. We actually looked at a couple of different signals to detect which ones are the best for the segmentation. So for example, we have the force torque at the wrist, we have the position of the hand, we have the high frequency vibrations in the fingertips, as well as the pressure signals. Once we have a segmentation, then we also want to learn a skill for each one of those. And for each of those segments, we extract a goal position as well as a desired force for that segment. Using this information, we also learn a goal detector. So the goal detector is a classifier which predicts whether or not the robot has reached the goal given the current tactile signal. And for this, we again use spatial temporal hypermatching pursuit features together with SVMs. Here you can see an example of a signal traces from one demonstration. So on the top, we have the positions. We then have the high frequency vibration signals. We have the electrode values, which give us the skin deformation. And we have the force torques and the forces from the wrist-mounted force sensor. We've also have these dashed lines, or these vertical lines, which indicate sort of the ground truth, which are hand labeled for when these mode transitions are happening. You can also see these X's and O's. So these are actually the points where the robot's segments using the change point detection. So you can see, for example, the surface and the groove are probably segmented, but we have a false positive here between. And for the groove corner, we have a false negative. So it didn't detect that because it's much more of a smooth kind of transition. It's not quite as sharp, although sometimes we do detect it. Here you can see the results of the segmentation. So on the top, we have the success rates for the different mode transitions, and on the bottom, we have the false positive rates. Using, for example, just the position data, we get fairly poor, especially for transitions like the surface and the groove. However, using the position together with the tactiles, that's both the electrodes and the pressure, we get this orange bar, which tends to be amongst the best performing. So using position together with tactile sensing seems to be a good way of actually segmenting these skills. As I said, we also learn a goal detector. So in this case, we're learning these from 35 trials. And here we have the classification accuracies for the different mode transitions. So some of these are very high. So the surface, the groove, the bottom of the hole are very distinct events. And so we get a very high classification accuracy for these. For the top of the hole and the groove corner, these are a little bit more complicated. They're not quite as distinct. So we have slightly higher. However, overall, there's still very high classification success rate, which is very good because it turns out the goal detection is actually really needed to make this skill robust. So when we execute the skill, just one skill after the other, there's a number of errors that often happen. So for example, we often don't reach the actual bridge, or we don't actually reach the corner, or we don't actually get to the bottom of the hole. And so if we don't actually detect for the goals and just try doing an open loop, then we're going to quickly run into problems. However, with the goal detection, it allows us to actually detect when we don't reach a goal and try the skill again from the current location. So So for example, here we have an example where it doesn't reach the hole. And in this case, it's not using the goal detection, so it's just going to keep going, and ultimately it fails to perform the task. However, if we now instead have the goal detected here detects it didn't go, it tries again to get to the groove, and then it can actually perform the task from there. So show one more time. So there it detects that it didn't reach it, and then it tries again. We can see the same thing also for the reaching the corner. So for example, here it's got into the bridge, but then it doesn't quite push it far enough to go past the corner, and so when it tries to go to the hole, it applies a very large torque. If we then instead actually have the robot detecting these goal events, then when it gets to the groove, it goes along, detects it's not quite there, goes a little bit further, and then it can perform the task now successfully. So using using this approach of re-attempting the skills, if it detects that it hasn't reached the goal, we can actually perform this task very robustly. In the future, we're going to be looking at actually using branching paths and different kinds of mode transitions for more complicated skills. So in this talk, we looked at predicting errors both for on the context of the fingers, as well as sort of between the object and environment. We also looked at how we can actually segment tasks into modes, so that we can learn to detect the transitions. And before I finish, I'd like to thank all the PhD students whose work I've been presenting today. So that's Yevgen, Carol, Artem, and Harry. And with that, I'm at the end of my talk, and I look forward to your questions.
First part of the talk about the regrasping and the policies.
Yes.
You showed a table and you mentioned that you combined policies. How do you do that?
Well, we combined the samples. So we took the samples from the individual ones. We then have more PCA components there as well, and then we put them into the neural network.
So you're saying you're pooling the training data and
Yes.
developing a whole new policy?
Yes.
Okay, you're not taking individual object-specific policies and then like averaging them? Or
No. So this is effectively a self-supervised approach.
For the vibration, what is the frequency range you know?
I think, Jeremy, you're probably better. What was the
Question.
question?
The vibration range, what you are doing?
It cuts off at about like 800 hertz or 900 hertz or so. So it's like mechanically filtered and digitally filtered. It's designed to match the pitch.
So only very narrow frequency band, or you are looking at a broader frequency?
Oh, it goes down to like 5 or 10 hertz. Or at least the PAC, which is amplified more. So its sensitivity is between about 10 to 800 hertz, but we could also do low frequency, larger amplitude vibrations. I think at about 200 hertz, it can sense vibrations down to 80 nanometers, which is pretty good.
80 nanometers?
Yeah.
So Oliver, you showed for the grasping, regrasping, you showed examples of objects which have regular shapes. So I was just wondering, can you comment on a little bit what would it generalize to objects with like very irregular shapes?
So I mean, there's kind of the assumption that if you're going like the tactile signal is going to give you a little bit of information about the shape, and then that'll allow you to predict it. So if it was, for example, you had two objects where one of them is like a sphere and one of them is like a sphere where you hollow out the parts between, then that would probably cause problems.
Right.
So I think one of the challenges going forward is really how do we combine sort of contextual vision information together with this tactile information, so that we can kind of combine the two and then sort of be able to differentiate different things.
Right. So for the zero regrasp case,
Yes.
what information did the robot have?
So that is just a sort of randomly sampled graph.
Randomly sampled.
Yeah. So we didn't want to sort of bias it towards any specific.
Okay.
So thank you, Dr. Kroemer.